With all of the basics of Zephyr out of the way, we can finally start looking at some application examples. But before we do that, I'd like to take a moment to demonstrate how you can enable step-through debugging, which is crucial for many complex embedded projects. In reality, there's nothing special about Zephyr's debugging capabilities. It relies on vendor-provided tools and open-source programs like OpenOCD and GDB to help developers debug their code. We just need to see how to connect them together for our ESP32 board to start debugging. Up until now, we focused on the various tools in Zephyr to help build device drivers and connect application code to hardware. Before jumping into applications, we'll take a moment to demonstrate how to do step-through debugging. The ESP32S3 comes with built-in debugging hardware that allows you to stop the processor, step through lines of instructions, and peek at memory values. In other processors, you might need a separate piece of debugging hardware, usually something that talks over the JTAG port. Our ESP32S3 Dev Kit C breaks out a separate USB port that can be configured to talk to this hardware debugger. We'll connect to that port from our computer and control the debugger using an open source program called OpenOCD or the Open On-Chip Debugger. This program has support for the ESP32 along with many other microcontroller architectures. You can directly send it commands to do things like pause execution and step through instructions. However, it has no knowledge of the code, which is where GDB comes in. GDB stands for GNU Debugger. It's another open source tool that helps users monitor the execution of code. OpenOCD runs a server and we can connect GDB to it as a client. As GDB has knowledge of our code, we can do things like set breakpoints and monitor variables. Because we're running our development environment in a Docker container, we can run GDB in the container and have it connect to OpenOCD running on our host machine, which in turn talks to our dev board over USB. Some operating systems still don't support passing USB through to a container, so this is the best option we have right now, assuming we want this course to work across the major operating systems. Up until now, we've been doing everything with the UART port on our ESP32S3 Dev Kit C. This is the easier port for uploading code and printing to the console, but it's not connected to the internal on-chip debugger. So we need to move our cable over to the USB port. With your ESP32 board plugged into the USB port instead of the UART port, we can now look into doing step-through debugging because there is an onboard debugger on that ESP32S3. Additionally, the S3 chip has built-in JTAG circuitry, so there's no need for an additional debugger. In fact, that's the reason I recommended this board or this particular chip for this series. That USB port on the board has JTAG information. It can enumerate as a USB device, and it can give us serial information, whereas the UART port is just connected to a USB to UART chip that communicates back to our board. In our case, we are going to use OpenOCD to communicate with the JTAG adapter that's on the chip. That's going to run a server, and we are going to connect to that server using GDB. Now, Espressif recommends their custom version of OpenOCD, and it looks like a custom version of ESP-GDB, but I'm going to show you how to do it with the basic versions because those are fairly universal and great at debugging other chips like ARM processors. If we take a look at the ESP32S3, you can see that the USB pins are GPIO 19 and 20, and indeed it does have a built-in JTAG interface, so no need for an expensive external debugger. There's some information here about configuring the drivers. In my experience, this doesn't really work in Windows, so we will use Zadig to inject a new driver instead. If you're using Linux, you will definitely need to update your UDEV rules, otherwise your driver won't work. As I mentioned, we'll be using OpenOCD, which you can read more about it here. This is an open source debugger that talks using the JTAG interface or protocol. You can give it special commands, and GDB, on the other hand, is a client that will connect to OpenOCD and give those commands so that we can do things like set breakpoints and step through functions while looking at our code. On openocd.org, you can find the docs here that lists all the commands for OpenOCD. And in there, you can find a list of supported targets. A lot of ARM stuff And here's our ESP32 chips. Note that these were added fairly recently. A number of years ago, Espressif forked OpenOCD and maintains their own version. They still maintain it to this day. It has some custom commands in there if you'd like to use it, but we're going to use the basic one. If you look at the release notes for OpenOCD, the official one, version 0.12 added support for Espressif USB JTAG, as well as some of the Extensa architectures. This includes things like the ESP32s that we've been playing with. If you're on Linux or Mac, you can probably use your package manager of choice. Just make sure that you install version 0.12 or greater. If you're on Windows, you will need to use one of these precompiled binaries that you can find from GitHub, this xpack-dev-tools, OpenOCD xpack. This has a bunch of releases and you can get precompiled binaries for it. So if we show all the assets, you can find the Windows. I've gone ahead and downloaded that. There's no real installer for it, so you just unzip it and put it into your program files, which I've done here. If you go into the binary folder, you can find openc.exe. That's the executable that we will need. However, just because we copied into program files, Windows doesn't necessarily know about it, so we need to add it to our path. So if we bring up the control panel, we can go to System and Security, then in System, in the System tab right here, scroll down to About, click on that. Go to Advanced System Settings. That's going to bring up another window. In the Advanced tab of that, click on Environment Variables. You can also just search in Windows for environment variables to get here a lot more easily, but this is the official way to get here from Control Panel. It's a little complicated. From this, we want to modify our system path, which is user variables. You could do it in system variables, but I'm going to do it just for my user. So I'm going to double click on that. That's going to bring up all of the path information. So let's create a new one. Let's go to Browse. And we're going to find where we put OpenOCD. So this is in C. We're going to go to Program Files. We're going to go to xpack OpenOCD and the binary folder there. Let's say OK. So now Windows knows where that is. So we can close down all of these windows. In Linux and Mac OS, this should be a lot simpler, especially if you use a package manager. But if you try to install it through one of these precompiled binaries here, you will probably need to update your path as well. I did a little digging. Even though this is for the C3 version of the ESP32, I did run into this bug where the driver doesn't work very well in Windows. If you look through this comment, you can see that Windows likes to include this libwdi, and it will probably need to be updated because when you run OpenOCD, you're going to get an error that says something about libusb. To handle that, you will need to install Zadig. You've probably done this before if you've done a lot of embedded development on Windows, especially dealing with USB libraries or USB drivers. So head to zadig.akeo.ie and just download the latest version of this. Once you've downloaded, it should be an executable. You will probably need to right-click on it and say Run as Administrator, although I think Windows 11 notices that it should be run as an administrator, hence the little shield symbol here, and run that for you. Make sure that your ESP32 dev kit is plugged into the USB port, not the UART port that we've been using for the last few episodes. Go to Options, List All Devices, and you should see two interfaces for our board. One is the USB JTAG serial debug unit, that's interface 0. That should be the serial, that's the COM port, so we don't want to overwrite that driver. We want interface 2, so go ahead and click on that. In my case, I've already updated this driver. However, if you go back to this issue, what you will probably see is something like this, driver WinUSB. This is the driver that's not going to work with OpenOCD. Make sure that WinUSB is selected as the target driver here. You can flip through them like that. Drop this down and say Install Driver, and then click Replace Driver. Wait a moment while that replaces the driver on your computer. When it's done, you should see driver was installed successfully, and you should see the driver as WinUSB. You can go ahead and close out of Zadig. And if you're really curious, bring up the device manager, go to ports. You should see a COM port here that's different than the one we've been using because it's a different serial port on the ESP32 board. And if you come down to USB devices, you should also find this USB JTAG serial debug unit. If you click on that, you can get driver details. And we want this libwdi. Even though it's saying that this might not work, it should work in my experience because we updated the driver using Zadig. Close out of these windows in a command shell, or I'm going to use PowerShell for Windows. We can type OpenOCD-version. This should work in Mac OS and Linux as well. With any luck, you should see not that OpenOCD can't be found, but something like the version for OpenOCD. With our board plugged in, we should be able to type OpenOCD-F and define the board we want to use. That's going to come out of the built-in configuration files that are already in OpenCD. In this case, board/ESP32S3-builtin.cfg. Press enter. With any luck, you should see it connect to the board and it should start running a server. If it exits and you see errors, look into those. If you see something about libUSB, especially if you're on Windows, go through that process of updating the driver again for USB. But it says the server is running. Now we can connect to it with GDB, which is a separate program. If you were curious, you can go into the OpenOCD installation. So that was in Program Files. Go into OpenOCD, under Scripts. You can see where all those config files are. So under Board, we can find our ESP32, which is right here, and that's the built-in. In fact, we can open that and you can see how OpenCD sets up its configuration files in order to read or talk to a particular board or chip. But we don't need to mess with these. Note that OpenOCD just supports the ESP32S3 for us, and we are ready to go and connect GDB to it. Leave this console open because that's running our server. In another console, in this case another tab, I'm going to go ahead and start our Docker image for our Zephyr container that we've been using to develop Zephyr applications on. Normally we've been running this by exposing ports 22 and mapping that to 2222 on our host machine in order to allow for SSH connections. That's what we've been using for developing. We're also exposing port 8800. That's if you want to use, say, a browser in order to use the built-in code server that's on that container. OpenOCD needs another connection, so we're going to expose port 33333333 as defined by OpenOCD. You can probably change it, but you see when we fired up, by default, it listens on port 3333, so we have to expose that so that GDB inside the container can then connect to OpenOCD that's running on our host machine that is connected over USB to our board. So with this, let's go ahead and fire up that container. We then want to connect to it with VS Code. It's going to ask for our password as it's been doing. And with that, everything's fired up. We can talk to OpenOCD. Because it's opening this workspace file, yes, I want to install the recommended extensions. Let's close out of these extension pages. And we will look at our files. In fact, I'm going to go to a terminal real fast. Espressif does provide its own version of GDB. The basic one won't actually end up working for us. We need the Espressif provided version. If we go into toolchains, one of the things that we downloaded when we initially installed Zephyr is this Zephyr SDK, which includes a bunch of things like compilers, cross-compilers, linkers, and debuggers, in our case, GDB. So let's go into that SDK. You can see how we installed pretty much just the Extensa Espressif versions of everything here. If you install the full SDK, you will have like ARM cross-compilers here and basic versions of GDB as well. Let's go into this ESP32S3 Zephyr folder, and let's take a look in here. You can see that this is another chunk of code for us, but let's go into the binary folder. And sure enough, here are our compilers. You can see GCC, CPP, C++, as well as GDB. Custom versions of GDB are included in this SDK, and that's actually what we want to use specifically for our ESP32S3. For most of this episode, we're going to go back and look at our very simple 01 demo Blink because it is very simple source code and allows us to step through and see how to work with both OpenOCD and GDB. Let's head into 01 Blink, and we're going to just call our normal build function with West to make sure that our build directory is up to date and we're ready to flash that code. Once that's done, make sure you have no errors. And if you go into the build directory in Zephyr, we've been using zephyr.bin to flash. We will still need to flash with that, but the .elf file contains extra symbols that the debugger, in our case GDB, will be able to look at in order to map what's going on in the processor, the actual execution, the memory, to what our code looks like. So that's the magical connection file for GDB, so we need to call GDB and pass it that file. We'll do that by running GDB manually. Specifically, we need the ESP32S3 version provided by Espressif. So we're going to run that program, and then we're going to pass it the elf file in the build directory. So start that up, GDB will run. Note that GDB is its own shell. We need to type manual commands here. Target remote tells us to connect to an OpenOCD server or some type of debugging server. In this case, it is OpenOCD. And we're going to give it the address. This could be an IP address, so this could be a different computer on your network if you want. But in order to do it internally with our host machine, within a container, we have to use host.docker.internal to essentially be localhost, but it's for our host machine, and then we give it the port 3333. With any luck, you should connect to that. If you bring up OpenOCD in your other terminal, you should see that it accepted a connection from GDB. So now we are connected from GDB to OpenOCD. In many cases, you can use GDB to load the binary or the ELF file directly onto the board by going through GDB. That would just be done using the load command. However, I find that this fails with ESP32. However, if you are using the forked version of OpenOCD from Espressif, they add a couple of special commands in here. And remember, this is OpenOCD, so we need to send that command to OpenOCD. To do that, you'd use the monitor command. Much like the -- that we saw with West build, this says whatever comes after monitor, send that command to OpenOCD. So we're not sending a GDB command. Monitor is a GDB command, and then we would say program ESP to send the program ESP command to OpenOCD, and it would have to be running that very special version of OpenOCD. In this case, you would just send it the path to zephyr.bin, and you would say verify. Note that this is not the path to zephyr.bin relative to where we're running this from GDB, so it is not in the container. Remember, we're sending this whole command to OpenOCD, which is running on our host machine. So we'd have to tell it where to find that bin file relative to wherever OpenOCD is running. It's a little confusing. Honestly, I find it easier just to open up a new terminal and send in the binary file manually. At least from this setup. If you're not working in a Docker container, this is probably a little bit easier. So I'm just going to flash it manually from my terminal here. I'll activate my virtual environment, and I'm going to call the ESP tool. Note that the port is now different. We're not using the COM7, or whichever serial port you've been using. It's a different port on our device. You could flash it through the UART port if you wanted to, but I'm just going to go ahead and demonstrate that you can flash it through that USB port. So I'm going to use COM6 instead of COM7. The rest of this is the same, and I'm going to point it to the O1 demo blink and that zephyr.bin that we generated during the build process. So let that update on our device, and let's minimize this and come back to GDB. This is not going to work. If we try to send this, you're going to see invalid command program ESP. Remember, you need to be running that forked version of OpenOCD for that to actually work. But with the bin file already loaded, we can use monitor, and you will sometimes see this shortened to mon. And we can send reset run. We're going to send that reset run command to OpenOCD. That is going to tell the processor to reset and start running the whole program from the beginning. You can see that it says core was reset. If we bring up OpenOCD in our shell over here, you can see core was reset. And because there's two cores, you'll see 0 was reset, 1 was reset. And because we said reset run, it starts running the program right after that reset. Now for real debugging, what we want to do is reset halt. So that sends the reset command, and now the LED should stop blinking. Sure enough, if we go to OpenOCD, we see that the cores were reset again, and the program is no longer running. From here, we can use GDB commands to step through our code. I'm showing you all of this from the command line first, so you get a sense of how this works, and then we will link it up to VS Code so you get that nice graphical debugging where you can set breakpoints using your mouse. To run from wherever we are, in this case it's just the beginning of whatever program's in there, we're going to say continue. Notice that it freezes up this terminal, so we just click Control-C, and that stops the CPU from running. Remember, we loaded this program onto CPU 0, so sure enough, CPU 0 stops. Let's bring this down a little bit. Let's go into our code. So let's go to source and main, and we can take a look at this. We can now set breakpoints. To do that, we use the break command, and GDB knows what to do with this. Main is a very common one in GDB, and that says go ahead and set a breakpoint. to the main function. You notice that it sets a breakpoint in the file. GDB is aware of the file because of that elf file we're using. Remember, we use that as a parameter when we fired up GDB, so it knows it's connected to this code. And it's going ahead to set a breakpoint at line 10, which is just after this main. So it's in the entry point here, and it's about to execute our main function. We can go ahead and set one to line 30. So if we scroll down here, that's going to be at this print K, so just before that executes. And let's try at 33, which is right here. Notice that it doesn't set at the line we set, it sets it at 34. It's a little bit off. What you'll find is that the compiler will often optimize away lines. So this line might not exist in the compiled code because the compiler optimized that away. Feel free to dig into the compiler settings so you can try optimizing to different states, because compilation is usually set to optimize for generally space or speed when dealing with embedded systems. I won't dig into that here because I'm just demonstrating how GDB and OpenOCD work so that you can start debugging. If we type info breakpoints, you can get a list of all of the breakpoints that have been set. You can see where they are. So if you bring up your code, you can look into your code and look for those line numbers. And we can say delete to get rid of this breakpoint and the number. In this case, let's get rid of number 3. So if we go to info breakpoints, now we just have those 2. Let's try setting one to line 39, which is down here at this sleep. You'll notice that there is no line 39, even though it looks like it's here. That's because once again, this has been optimized away by the compiler to make something a little more efficient. And no, we don't need to make this pending on future shared library load. Our current execution point should be long before main. It's in that setup code that initializes the threads and whatever drivers you have. So let's go ahead and continue. That's going to continue execution until it hits our main breakpoint. So you notice that execution continues in the actual physical device until it hits our first breakpoint, which is here at line 10. So it should have stopped at this main, but I think I see what we did wrong here. If I scroll up, we reset and halted the controller. I said continue, and then I controlled C to stop execution, and I forgot to reset the controller because we then set breakpoints. So now it's just in this main function executing. So let's try mon reset halt. Let's try continue again. So now it starts from the beginning. There we go. So now it's stopping execution at line 10 just after it enters main. So let's do continue. This is where it hits the first breakpoint within main, that is 30. So it's just before this print K. We can use the print function to print out variable information. So if we say print state, because that is the name of one of our variables, sure enough, that is equal to 1. Just in case you don't believe me, print sleep time ms is 1000. That's this global constant that we set up here. And what happens if we just print something? No symbol ASDF in current context. So it needs to be related to a variable or a symbol that we're using in our code. You can also say info locals in order to discover which of the variables are in scope for the current execution context. In this case, the return variable has been optimized out. Once again, we cannot find information on that because the compiler said, you know what, I'm just going to inline all of this. But we can get information on state because that has already been changed. Even though it starts at 0, we stopped execution right here. That's been updated to be 1. We can look at memory. The X function allows us to do that. /1, this first parameter, loads the number of memory units. In this case, it's 1 word, which should be 32 bits. You can make this like 10 or something else if you want to look at big chunks of memory. And then the X behind it tells us which format to use. In this case, we want hex, very common to do with memory. And then 0x and then the location of memory. We saw this before when we were looking at device trees, but 60004004 is the location of the GPIO register, so we can examine the state of that GPIO. So we'll look at it, it's all zeros right now. That's because GPIO pin set has not been called, so we actually haven't updated it even though state is set to 1. So we're right here in execution right now. We will come back and look at it once we've run through this. Let's type list, and you can get an idea of surrounding code. We're at about line 30, and you can look at the code around it, and you can match it up with your files. That's usually very helpful if you get confused what's going on. You can step into something using the step function. So we just say step. It executes a line of code. It goes in here. Notice that you will sometimes run into this can't access memory addresses. It can't insert breakpoints. Some things get optimized out. So GDB might have some trouble going into a particular function. but in this case, it looks like we were able to step into print K. You can step over with next, so that runs whatever current function is without stepping into it. And that executes there. We can list again. Sure enough, we're still in print K, but we've executed one more line. And if you want to finish and get out of this function, so step out of, you just type finish, and that runs the rest of the function, whatever lines are in there, and that should go back to whatever the caller was. In this case, you see we kind of get stuck in this context wherever this is. So sometimes this might not work, especially if it struggles to set breakpoints due to optimizations. Since we're stuck here, we don't know where we are, we can use this backtrace function to get an idea of where we are in the call stack. So this first one is the function we're in, so we're in print K, and that's being called from within main. If finish still isn't working to get you out, I find that setting a breakpoint can help. Just like we did earlier, you would just call the break, give it the file and the line number, and tell it to continue. In this case, we should continue until that next breakpoint. So we've come back around. We're back at line 30 after going through that while loop once. Your LED should be on because it executed pin set with state equal to 1. And now let's go through our previous commands to look at the memory address. And sure enough, that bit is set in memory because we wrote to it with GPIO pin set DT. Once you are done and you want to disconnect from OpenOCD, you can just type detach and you should be disconnected. So we can go look at OpenCD and you can see that it dropped the GDB connection here. Feel free to reconnect, play around with it, understand a few of the commands, look at the documentation. Once you are done, type exit and you are done with GDB. As I mentioned, if you want to learn more about GDB and how to use some of these commands, the sourceware.org GDB documentation site has some really good information. This is better as a reference guide, so you can go to the GDB user manual and you can understand all of the commands that are in here. So there's command syntax, there's command settings. Feel free to work through this. Not a great getting started guide. For that, I recommend going to beej.us/guide/bggdb. And this is a really good getting started guide on how to use GDB from the terminal. If you're like me, I want to connect it to VS Code so I don't have to keep doing stuff from the command line. Even though it's really powerful, I want to be able to use a GUI to do things like step through functions and then actually set breakpoints in my code while I'm looking at the code. Let's go ahead and close our terminal. We don't need that right now. You will need a couple of extensions to make this work. If you are using my repo with the pre-configured Docker file, that should recommend a few extensions for you. If you don't have that or you're installing this on your own, at the very minimum, you're going to need the C++ that comes with Microsoft IntelliSense that allows us to do things like stepping through code, viewing definitions, navigating a lot more easily, and color coding very nicely for you. You will also need some sort of hex editor. The Microsoft one seems to work just fine for this. This is what allows us to do things like view the memory. Now to set this up, you will want to go to your files. You will want to go to your .vs code within your workspace, so the top level of your workspace, and create a launch.json. I've already created this here for you, so I won't go through the individual steps, but you are welcome to take it from my GitHub repository and use it for your own purposes. We define the name, the type that we want to use, in this case C++ debugging using GDB, and then on launch we're going to define our own input, and the inputs are defined down here, and we want to ask the user where is that elf file. Here we say stop when you hit the entry point, so main, and we give it the context of the current working folder, and we want to give it the path for GDB. In this case it's that ESP32S3 specific one, so note that this is for the ESP32S3. You could set up another configuration if you want to set it up for different GDB targets. I've also provided the location of OpenOCD. In this case, it should be running on localhost that's outside of this container. And then we give it some optional commands to do things like enable pretty printing. So with that configured, we should be able to click this debug and run option here. With this drop down, you should see it here. Note that if you don't see it and you've set up launch.json, you might need to reload the window. So in the command palette here, you would just type reload window. That'll reload things. If you're in the container, it's going to ask you to reconnect. So it should bring it up as a run/debug profile. So we'll click on that, and then we can click on run. It's going to ask for the location of the elf file. And that's the input that we set up. Notice that's defaulting to a previous one that I used. We want to do it for 01 demo blink. So go into build, go to Zephyr, find that ELF file. If you know where it is, feel free to type it in. And we are going to right click and copy path. I find that using absolute paths here saves some headache, so we're going to paste that in and we're going to press enter. It should fire up for us, and in fact we stopped here last time. We didn't reset the processor. So to reset, we're going to go up here and click this restart, and that looks like it runs all the way through until it hits our breakpoint. So let's try setting a new breakpoint here. Right after main runs, let's reset. And it looks like we're having some bugs where it's not catching those breakpoints. Okay, so I don't think we did this correctly, because you'll see down here in the output, it keeps coming through there. And if you come down to debug console, you can talk to GDB here. Info breakpoints doesn't work, so if something's really broken here, let's do a reset halt. After some poking around, it looks like it's stopping here because these breakpoints were picked up. Must have been from when I ran GDB previously, so let's get rid of these breakpoints. Let's try to reset the processor. It's still stopping here, which is really interesting. What's really interesting about this is I've got the two CPUs and I can actually run them independently. So if I just click run it again, okay, the program's now running and my LED is flashing. So let's pause that, wherever that is, and I can come back to main. I'm going to put a breakpoint on 30. You can see that down here. I'm going to run it again. It should stop at that breakpoint. Now I can step over. That just allows me to execute one line at a time. And I'm going to come back around to this print K. I can step into. It'll go into that function. I can step over, goes through that. I can also step out of. So that's the same as finish. It should come out of that. I find that this works a little better than the GDB finish. And I'm back over to this set pins. Right now, if I hover over this, you can see the actual value of that. It is 0. Under variables on the left side, you can see that return was optimized out and state is indeed equal to 0. You can also view the CPU registers if you want to get some information about what's going on there. I can add a variable to the watch list. In this case, let's add state. You can see that's set to 0. Unfortunately, there is no easy memory viewer like you have in GDB, so you usually have to rely on that. You can click on the binary file next to the watch or any of your variables. That will open up that area in memory so you can view what's going on. And this is why you need that hex editor installed. So the way to view memory for something like a register is in this debug console. You can do exec to execute a GDB function. In this case, it's that x/1 and then X for hex 60004004. And you can see that has been set because we haven't updated the register yet with 0. Once you are done, you can click the stop button. You can also click reset to restart your controller. It will run up into that halt point and we can click continue to get to our breakpoint. And then when you're done, click stop and you'll exit out of the debugging mode and we can close that down and go back to our file viewer. Hopefully this helps you get started with step through debugging. It is a little complicated to set up, but it can be very powerful once you do. Your challenge is to get print K working over the USB port instead of the UART port. Okay, this is more of a device tree challenge, but it's still good to test your knowledge of this. Start with the Blink demo that we did from the very first episode. Then as a hint, if you go to Zephyr, if you go into boards, let's find Espressif, wherever that is. Let's go to the ESP32S3 DevKit C, and then there's the DevKit C Pro CPU.dts. If you look in here, you can see that the Zephyr console is set to UART 0. So this is your hint for figuring out how to make the console attach to the USB port instead of the UART port. Once you have it done, I've got my solution here on 07 solution USB print. I should be able to flash it, in my case to COM6, which is the USB port. That should flash, and then I should be able to open up a serial terminal, not to COM7, which is the UART port, but to COM6, that same one. And sure enough, it should be spitting out the same information about the LED state that we saw from the first episode. That's how you know you did it correctly. For the rest of the series, I'll switch back to using the UART port on the dev kit, but feel free to upload programs to the USB port instead. Just remember that you'll need to change the overlay files to make the USB port the console going forward, just like you did in the challenge. My hope is that at this point, you have a decent understanding of the device tree, drivers, and debugging. I consider those to be the fundamental skills needed to actually start developing in Zephyr. With that, we can start looking at various applications over the next few episodes, starting with multi-threading. Good luck and stay tuned.